let's recall that as the battery or as the charge carriers leave the battery, what happens is their potential energy remains the same until they hit the light bulb. Then that energy is used up as internal energy to give off light and warm up the filament itself, and that drops off the potential energy of the charge carrier. Then when it's returning to the battery, it's got no potential energy, it's just being pushed forth by the electromagnetic field in the circuit. And then once it reaches the battery again, the battery charges it up by doing work on the charge carrier and giving it potential energy until it gets back to the actual lead, and again we go through this circuit. Now, a schematic diagram is defined as a visual representation of an electric circuit, and you simply use standardized symbols for this. And the idea to standardize things is so that everybody can read them the same way. So this could be some sort of a power source, a random light bulb and a random light bulb, and no matter what the power source is, whether it's a battery, whether it's a generator, and this is a light bulb, it doesn't matter what the wattage is on the light bulb or what the voltage readings are on the battery, but the schematic would look the same. So again, a schematic is just a representation or a model using physics. Next, we'll take a look at some of the components used in a schematic, and first and foremost are wires, because wires connect everything. And since wires really have negligible resistance or no resistance, we can represent them just using a straight line. Now, when a wire is turning, we use a right angle in the diagram, even though a wire is curved, right? And remember that wires are just, copper wires that conduct electricity. Second are resistors, or what are called circuit loads, things that control the current in the circuit. So a resistor itself is able to use up that voltage in a sense. So we think of the fact that it slows it down. So we put a little squiggly line here to show that it's being slowed down. It's taking a slower path suddenly along the wire, and then the current continues through there. Next is a bulb, or a lamp in general. And a bulb is really just a resistor, but we specify that just by putting a circle around it. Okay, so you just put a circle around the resistor, and you could draw it the way it's shown here, or you could simply even draw it like this, with a circle around it. Fourth is a plug, and a plug has two prongs on it, one positive terminal, one negative terminal on the prongs. So we can draw it this way to represent that. This is the positive terminal, this is the negative terminal, or it could be drawn like this. This is one of your more common representation. A battery shows just simply two lines, one line larger than the other though, again showing a positive terminal and a negative terminal. Now some batteries, like computer batteries, like lithium cell batteries, are made with more than one cell. So if there are multiple cells in a battery, then we have to consider the fact that we have to draw those several cells here. So this would be a battery with 3 different cells in it. Finally, the last thing is to take a look at it as a switch. And a switch just opens or closes a circuit. And this is an open circuit because the switch is open. This is a closed circuit because the switch is closed. So an open switch would look like this, and a closed switch would look like this. The 2 little circles here are indicating these junction points right here. So these little points here in the junction are those little circles right there. Now an electric circuit is simply a set of electrical components connected to provide one or more complete paths for the movement of the charge. So the charge may go along one path, but there may be several paths to look at, and we'll see that when we get to series and parallel circuits. But what a circuit really consists of, a circuit consists of 2 things at a minimum. It has to have a potential difference. The potential difference is really just the source of energy. Without a potential difference, there's nothing to establish the electric field to cause these charge carriers to move through the circuit. And then second, you need a load-bearing element, something like a light bulb or resistor that can dissipate the energy. So there's all this energy that comes from the potential difference, and if there's nothing here to use up the energy, what will happen is the wire will try to use up the energy. And we'll talk more about that, and we'll talk about something called a short circuit and what happens there. Next, let's take a look at a closed circuit. And what a closed circuit really is a circuit where the electrons can move from one terminal to the other, and a current can exist when the switch is indeed closed. So when we have a circuit and we think about a switch here, so let's say it was just a simple switch that was open. So we've got our potential difference, and we've got our load-bearing element. So this is our basic circuit. Now we introduce a switch. As of right now, what happened is the electrons would want to move through here, but they wouldn't be able to complete the path. So because this path is not completed, there's no EM field that's established. But the minute the switch is closed like this, and this is no longer open now, it's closed, what happens is it completes the path. So the potential difference starts to generate, or it starts to give energy to the charge carriers and pushes them through this circuit here. Now a light bulb, what happens is this. This is really kind of interesting to think about. the current enters the light bulb through the base connection right here. So it takes a look here, it contacts the base, so here's the bulb, right? Here's the bulb itself, this is metal, this is metal. It goes through this wire, it connects to the actual bulb right here. Then it flows through the bulb into the filament. And when it passes through the filament, the energy is converted to thermal energy. And again, this is not all bulbs are this way, right? We know that some are gas bulbs, those incandescents now. And light energy, okay, so thermal and light energy. Then it continues through the circuit. There's no energy in the charge carriers. The charge carriers continue through, they hit the side of the bulb, then they go into the side of the contact in the actual base here. Okay, or back out the side of the metal socket, and once they travel through the metal socket, they come out the other terminal and back through. And what happens is then those charge carriers re-energize or gain energy from the power source and continue to go through. And it creates a circuit. Now this light bulb is an example of an old school light bulb. Now we see so many light bulbs nowadays that are incandescent that use things like gas and chemical reactions to generate light, and they don't give off heat. So that's why this says thermal energy, not all bulbs, because not all bulbs give off thermal energy or give off heat. Something that we should note here is that if these two wires were to touch, now clearly they're insulated here, right? There's rubber around each of them. But if the two wires were not covered in rubber and they were to touch, what would happen is this. You'd have your power source right here, and it would generate a flow, right? But what if they touched somehow? Like what if the wires got bent and they somehow crossed and then came back? Well, what happened is this. The charge carriers would want to take the path of least resistance, and all this energy in the charge carrier would go like this, and it would come right back through. It wouldn't actually go into the light bulb. So this would create a short, and what happens is the bulb would never get any energy. And without some sort of a load-bearing element, these wires, and I'll highlight them in red, this portion of the wire that crossed would start to heat up, because it would use up all the energy in the charge carriers, and when this heats up, it would start to ignite, and you would have a fire. And what happens there is that causes a lot of melted wires and simple house fires that you have from these short circuits when you have old wires where the wire rubber casing is old and deteriorating. Finally, we'll take a look at the term EMF. An EMF is a source of energy that can cause a current to flow in an electrical circuit. And we've talked about this already, but the idea of an EMF is what I want to discuss now. An EMF is interesting to think about because the terminal voltage is actually slightly less than the voltage supplied by the EMF. And the reason for this is because of this small internal resistance here that's really occurring in the battery. So a battery like this battery, for example, a 9-volt battery. And a 9-volt battery, if you measure with a voltmeter, actually doesn't give off 9 volts. The difference the terminal voltage that it would give off would be like 8.9 volts. And that little difference is because of this small internal resistance. Now, we consider this to be negligible because it's so small. But really what we're saying is that conservation of energy is what leads us to the fact that the potential difference across a load-bearing element is really equal to the terminal voltage. Okay, so the terminal voltage here, the voltage between these two terminals, is equal to the voltage across this load-bearing element. Although, again, the EMF provided is really a little bit higher than what this bulb is going to feel because of the small internal resistance. First, we're going to talk about the types of circuits that exist. And first, there is a series circuit, which is the basic circuit. And a series circuit is a portion of a circuit that provides a single conducting path without any junctions. What we'll see here is that the path of the charge carriers would flow through each element in the series circuit and come back to the other terminal. Whereas in a parallel circuit, there are two or more components in a circuit that are connected across common points or junctions, and these provide separate conducting paths. So for example, what we'll have is part of the charge will go through here and come back through, while at the same time another part of the charge branches off and goes here and through the second bulb. Another part of the charge branches off here and goes to the third bulb. So these all occur on different conducting paths. Start with a series setup here. And we're going to take a look at three things in series. We're going to look at the current, the voltage, and the resistance to understand our laws. And the first thing to notice is that the current through or across each resistor is the same. It's like the flow rate of water through a pipe. If you had a pipe set up, and you had sensors here, here, and here, and those sensors were able to sense the current of the water here, and then here, and then here, there'd be no change in the current. They'd be occurring along the same path because the water is still flowing through the same location. So what we say is that the current in a series circuit, again, is equivalent across each of these resistors. So we'll say I1, I2 equals IN. IN meaning as many resistors as there are. So if there were 10 resistors, we'd list I equals I1 equals I2 equals I3 equals I4, etc. And this is important to know when we do some calculations in a minute, that the current across each resistor in series is the same. Now for the voltage, we can think about the fact that the potential difference across the battery is really equal to the potential difference across the total load, or the sum of the load across each resistor. And what that means is that the voltage is equal to the sum of the voltages, or the voltage drops, across each resistor. So if there's 5 or 6 resistors, each of them take on a certain amount of voltage or potential difference, and as a result, the sum of all of them is equal to the potential difference provided by the battery or the source of energy. Now the third part that's a little bit more confusing though, and we're going to derive this third part, is resistance. And if we remember that V equals IR, Ohm's law, applies to each resistor, so for 2 resistors what we can say is that V equals V1 plus V2, and that comes from here. Imagine we just had 2 resistors, right? We could replace each of these V's with IR. So the current across the entire circuit times the resistance of the entire circuit, and I'll explain what EQ means, is equal to the current across the first resistor times the resistance across the first resistor, plus the current across the second resistor times the resistance across the second resistor. And now what we have to do is take a look back at our current law. Our current law said that the current were the same throughout each of these resistors. So this I, and this I, and this I, these are all the same. Well, if all those I's are the same, what I can do is just write them all as simply I. So what happens is this becomes, without any subscripts, right? And now I could simply cancel all the I's. And it's not obvious maybe, so maybe just factor it out so you can see. But really just factoring out an I. And then the I's cancel on both sides. Leaving behind our law of resistance in series, which states that the equivalent resistance of a circuit is equal to the sum of the resistors in that circuit. So what this means really is that if we had 5 resistors, we could really, and this is mathematically speaking, replace those 5 resistors with one resistor that is equal to the sum of all the resistances across those 5 resistors. So if we write this law out, that was just for the example of 2 resistors, it would say the following. The equivalent resistance in series is equal to, again, the sum of all of the resistors. So example 1 says a 9-volt battery is connected to 4 light bulbs as shown in the figure to the right. Draw a schematic representing this and then find the equivalent resistance for the circuit, that REQ value. From this then determine the current in the circuit and also find the voltage drop across each resistor. Now, we can see that the voltage or the charge carriers are leaving the terminal and going through each resistor in series here. So if I were to draw a diagram, I would start with some sort of a voltage source. Now I have the terminal, the positive terminal, and we remember that we're looking at the positive flow of charge with current, so I'll leave that. And we'll then enter the 7 ohm resistor. And it doesn't matter the way I draw this, I'm going to put 2 resistors on top. Then the 5 ohm resistor, then the 4 ohm resistor, and then finally through the 2 ohm resistor again here, and back to the negative terminal. Again, it doesn't matter if I had put, say for example, the 7 ohm one up here, and then 5, and then 4, then 2. Or maybe 7, 5, 4, and then put the 2 one up here. As long as they're really in the same order that we started with. 7, 5, 4, 2. 7, 5, 4, 2. Leaving the positive terminal. Notice I drew it going this way, whereas here it would go this way. But it really doesn't make a difference in this sense, as long as they're in the right order. Now, at the next part, I'm going to say I want to find the equivalent resistance of the circuit. And if I remember my law from a moment ago, this is what the law said. Okay, the sum of all the resistances. Therefore, I could simply say that I could replace this with one resistor that is the sum of all of them. So 7 plus 5 plus 4 plus 2 gives me a net resistance of simply 18 ohms. So this is what I can write in my diagram. Now, the voltage on the battery was 9 volts. So let me add that to my diagram in each spot. Now, if I know what the voltage is, and I know what the equivalent resistance is, I can determine the current in the overall circuit. So let's use Ohm's law, saying V equals IR, and therefore I equals V over R. V over R would be 9 volts over 18 ohms, which would be 0.5, right? 9 over 18 is a half. And my units are amps. So the current in the circuit is 5 amps. That's the current through all of the resistors, because remember, in series, the current in the circuit is equal to the current across each resistor. The last part we want to do here is to find the voltage drop across each resistor. Now, to do that, we have to think about the fact that each resistor also follows Ohm's law. So for the first resistor, we have this, but remember that the current, we don't really need this subscript of a 1 here. Why don't we need that subscript? Because the current is the same in series across each resistor. So if I want to find the voltage drop, I just simply take 0.5 amps times the 7 ohms in the first resistor, and I get 3.5 volts. For the second voltage, I'm going to do the same thing. Take the current of 0.5 times R2, so 0.5 amps times 5 ohms, giving me 2.5 volts. And let's take a look at the third and fourth resistors. The third and the fourth resistors follow the same law, IR3 and IR4. Therefore, we have 0.5 amps. Here we have 0.5 amps. This is times 4 ohms. And this is times the last rating of 2 ohms. So that gives me 2 volts, and this gives me 1 volt. So these are the voltages across each resistor. Now, the last thing we'll notice is this. If we sum those together, this proves our law from earlier. Our law from earlier said the voltage in series across the terminals is equal to the sum of the voltages across each resistor. So since we have 4 resistors rather, if we add these 4 numbers together, we end up getting a value of 9 volts, which was the voltage across the battery. So what we want to look at next is the fact that a series circuit requires all elements to conduct. And what you'll see here is this. If one bulb goes out, they're all going to go out. And you remember this from Christmas trees. When one of your light bulbs went out, the whole strand of bulbs would go out because they were connected in series. Now, today a lot of them are connected in series and parallel. So you'll see one go out and only a little section will go out. We'll talk about how that works when we get to parallel circuits. But what happens is the charge carriers want to flow, but when there's this opening, there's this gap, the EM field is no longer established, so it's not going to push the charge carriers through. So this creates an open circuit. Now, you might say, well, why would you ever want it in series then? It doesn't make sense if this could create an open circuit. But the reason is that sometimes it's useful if you want to regulate the current. And we'll see that a little bit later how this works, because if you notice a moment ago in the last example, remember the number for the current in the system was only ½ an amp. And we're going to see in a little bit, we're going to use the exact same example in parallel, and we're going to see that our current is not going to be ½ an amp anymore. The current in the circuit is going to be much greater than ½ of an amp. So if you need a low current, you want to regulate your current, you would probably choose partially a series circuit. Okay, but again, a lot of circuits now are made of series and parallel mixed together. Now for a parallel circuit, we'll look at the same 3 things. We'll look at current, voltage, and resistance again, but now it's in parallel. So think about, again, like water flowing through a pipe, but now think about this. Water's coming through this pipe, and now imagine the pipe branches off into 2 branches. What would happen to the current, right? There's a certain amount of current flowing through here, and if these pipe dimensions were the same, the current would dramatically slow down in each pipe. So again here, we're going to notice now for the current though, the sum of the currents across each resistor is equal to the total current leaving the battery. So we could say that I in the total battery equals the sum of the currents. Whereas last time, we said that the currents were equivalent across each resistor. Now it's not. Now we could say that if, there's a total current of, say, 10 amps, each of these resistors has part of that 10 amps. They don't each feel 10 amps of current flowing through them. The second law is the voltage law, which is a little bit confusing, but we'll try to explain it here by considering the fact that the positive terminal in a parallel circuit, I'll draw it at the top, but the positive terminal in a parallel circuit, right, so here's a parallel circuit, and this positive terminal here is connected to each lead, right? It's connected there and it's connected there. Now, what that means is that since it's connected to each bulb and not just the first bulb, that the voltage is going to be equivalent across each of these resistors. So we're seeing this now. So what we can say is that, if you want to just remember this, the current and the voltage laws are the opposite and parallel. Earlier these were all equal signs and these are all plus signs, whereas now these are all plus signs and these are all equal signs. Now to derive the resistance law, we're going to do the same thing as we did in series, except now we're going to notice that since obviously V equals IR, we have it this way, we can solve for I in that equation and say that I equals V over R. And now instead of writing V equals V1 plus V2 like we did in series, we're going to write out our current law. I equals I1 plus I2, etc. So imagine there's only two resistors, this is what we have. Well, that definition of current is voltage over resistance. So let's replace all of these with voltage over resistance, yielding V over the equivalent resistance equals V1 over R1 plus V2 over R2. But we recall from a moment ago that the voltage drop across all the resistors is the same. So these V's are all identical. So instead of V1 and V2 and V3, let's write it out again like we did earlier, but with just V in each of these. Again, earlier it was just I in each of them. Now it's just V in each of them. Well, again, what we can do is we can factor out a V on both sides. So this becomes V times 1 over Req. And on the right-hand side, this becomes V times 1 over R1 plus 1 over R2. These V's cancel on both sides, yielding what's called a reciprocal sum law. What we can say is this: the reciprocal of the equivalent resistance equals the sum of the reciprocals of each resistor. So as a law, it would look like this: 1 over Req equals 1 over R1 plus 1 over R2 plus ... 1 over Rn. So the law is pretty much the same idea. It's still a sum, but instead of being a sum of resistances, it's now the reciprocal sum of resistances. So example 2 is pretty much the same as example 1, but now we're looking at a parallel circuit. And we can see that it's parallel because the positive lead here, okay, or either one's positive, doesn't matter here, connects to this terminal, and then it connects to here, and it connects to here, and here. So we have this parallel circuit now. So what it looks like is the following. And each of these resistors here has its own branch, and it's in parallel. So this is 9 volts, this is 7 ohms, this is 5 ohm resistor, this is a 4 ohm resistor, and this is a 2 ohm resistor. So now we have to look at our resistance law. Remember that it's 1 over Req equals 1 over R1 plus 1 over R2 plus ... 1 over Rn. And this is going to be a bit confusing at first, because we have to do a little bit more math than last time. We end up getting, let's see, 1 over 7, plus 1 over 5, plus 1 over 4, plus 1 over 2. Now in this case, you can find a common denominator, come up with a fractional sum, and then take the inverse. Or it might be a little bit more useful just to add together those fractions and round to the nearest decimal. And the reason I say that is really just because it's easier to do it on your calculator than finding a common denominator. So if you add those fractions together, you end up getting approximately 1.09. So 1 over Req equals around 1.09. So how do you find Req? You take the inverse of both sides. Right? If you want to find 1 over something, you want to find Req, the invert that side, or the reciprocal. So you really want to raise this number to the negative 1 power. So Req is really 1.09 to the negative 1, or the inverse, which is really just 0.917 ohms. And this is really interesting to notice. Earlier, when we found the equivalent resistance in series, it was a value of, I think, 28 ohms, which is a much larger value than any of the values, or 18 ohms rather, 18 ohms, than we started with for each of the resistors. But here, the equivalent resistance is suddenly much, much less. And notice that this equivalent resistance here is less than all of these original resistors. The original resistors were 2, 4, 5, and 7. This number is far less than any of them. So what you can say is that in series, the sum of the resistances, or the equivalent resistance, is always going to be greater than any individual resistor. Whereas in parallel, the equivalent resistance is always going to be less than any of the original resistors that we had. Now let's draw the new circuit, what it would look like. So this new circuit would still have a positive and negative lead, but now we just have one resistor, and its resistance would be 0.917 ohms. This is still 9 volts. Now the next part says we want to find the current in the circuit, so we'll still use Ohm's law again, V equals IR. and solve for I equals V over R. But now look at this. The voltage over this really small resistance. Earlier we took a voltage of 9 volts and divided it by 18 ohms to give us a small current of half an amp. But now we're taking 9 volts and dividing it by 0.917 ohms, which means that this answer is going to be much greater, because clearly we're dividing by a decimal, so the number is going to get larger here. So you end up with a current in this problem of 9.8 amps. Huge difference than when we're in series. So in series, if we have resistors connected, the current is going to be much lower than the current felt when it is in parallel arrangement. The current again in series was 0.5 amps. The current here is 9.8 amps, almost 20 times the value of the current that it was when it was connected in series. And that's why earlier we said that if you want to control the current or limit the current, you would set up your elements in series to reduce the current. But if the current doesn't matter in this case, if the current can be a larger current, you could have them set up in a parallel arrangement. Now the last part we want to figure out is to determine the current in the current through each resistor. Current through each resistor. And the reason we're going to do that is because we remember our current law said that the sum of the currents equals the total current. So let's find the current across each resistor now. And to do that, we're going to say that current in the first resistor is equal to the voltage across the first resistor over the resistance itself. Now, remember that the voltage is the same across all resistors, so this is always going to be 9 volts, but the first resistor is 7 ohms. So the current in the first, or across the first resistor, will be 9 over 7, which reduces to approximately again, 1.29 amps. In the second resistor, we can find its current by taking V2 over R2. But remember that the voltage across the second resistor is still 9 volts. These are the same, notice, because our voltage law in parallel says that V equals V1 equals V2, etc. But the resistance is different in the second resistor, and that's a resistance of 5 ohms, giving us a current of 1.8 amps. And then we do the same thing for the third and the fourth resistor. Again, 9 volts over its resistance, which is R3, and that's a resistance of 4 ohms. That's going to give me a value of 2.25 amps. And then finally, the fourth resistor, 9 volts over 2 ohms, which gives me 4.5 amps. Now, if I take these four values of current, what I'm going to notice here is that when I add them together, they do indeed sum up to the original current in the problem. And the original current that we solved for was 9.8 amps from earlier. Remember that number. And our current law, remember, tells us that the sum of all the currents is equal to the original current, or the current through the whole circuit. And these four numbers, 1.29 plus 1.8 plus 2.25 plus 4.5, is indeed approximately 9.8 amps. The reason it's approximate is because we rounded earlier when we did the equivalent resistance, so there's going to be some rounding error in the problem. Now let's take a look at resistors in parallel, and they do not require all elements to conduct. So if one goes out, the flow of electrons continues through the remaining paths. And let's illustrate this. Imagine, if you will, that this did not exist, this entire path. It went out. Right? That bulb blew and there was no longer a path there. Well, it doesn't matter, because the voltage is still going to, or the charge carriers, the voltage will push the charge carriers through all the rest of these continuing parts. So even if all of them went out, except for the last one, you still have a completed circuit. This would still pass through this entire thing. So in parallel, if one bulb goes out or if one element stops working, the others continue to conduct that flow. So finally, in summary, let's take a look here. In series and parallel, the schematic in series looks like this, where the two elements are one after the other, thus the word series, they're in series. And when they're in parallel, we see that it branches off, and we can see these lines are parallel to one another, hence the word parallel. The current in series is the same across each resistor, whereas in parallel it's the sum. And then it's vice versa for the potential difference, or the voltage. The voltage in series is the sum of all the voltages, whereas the voltage in parallel are equivalent. So equals and plus, whereas this is plus and this is equals. And then finally, the equivalent resistance in series is the sum of the resistors, whereas in parallel, it's the reciprocal sum of the resistors. So if we take a look at an example here, let's go ahead and look at this. So we have an old school looking microwave here. Doesn't really look like a microwave, but that's a microwave connected to one of the outlets. Then we have a toaster and a blender connected to a splitter. So this is a splitter with 3 outlets on it. And what we're going to see is this. First of all, inside your house you have a circuit breaker with very minimal resistance. And what a circuit breaker does is it senses a very high current. If there's a really high current in the circuit, it will trip the circuit breaker and it'll open the switch in order so that your circuit doesn't have a short circuit in it. So it doesn't start to cause a fire. So a circuit breaker is really a safety feature. So that's all that is there. Now what happens is this. We'll see that the flow leaves the positive terminal. And it flows here. We look at the positive flow. And what happens is soon it breaks off first. So it breaks off into a microwave portion. This is the first outlet. And then this part goes to the second outlet down here. This is really one outlet that's been broken into 3 little prongs. So one part of it goes to the microwave. That's fine. But then the other portion goes into this part here. And what we'll see that really, this here is like a branching off. So this branch here and this entire branch here are in parallel with one another. But if we were to really just zone in on this section right here and forget everything else going on, what we'll see is that these 2 resistances are actually in series with one another. And it's not obvious right away, but it actually is true. Because the current is flowing here, and what will happen is the current will go through here, hit the toaster, come back around, hit the blender, and then come back through. So what we're going to see here is this is a little mini series circuit within a parallel circuit. So really we could simplify these two, and 41.1 plus 16.9 would give us 58 ohms. So in reality we could draw this circuit like this. Oops. And that's what this would look like, obviously, with the circuit breaker in place. And what we would have here would be, again, as we just stated, a 58 ohm resistor. Again, the sum of these 2 resistances, because remember in series it's a sum law, with this 8 ohm resistor as a microwave. And then what we'd have to do to simplify this parallel portion of the circuit would be to use our reciprocal law and say 1 over 8 plus 1 over 58. So what we're going to see is that what we really want to do is break down these circuits into series and parallel parts and simplify everything in series, then go to our parallel portion, simplify everything in parallel, and hopefully we'll be done there, or maybe we have to go back to series at the end. So let's take a look at an example of a circuit that's a little more complex than this. So in example 1, we're going to determine the equivalent resistance of this complex circuit shown, and then from this, we're going to find the overall current in the circuit. So step 1 would be to redraw the circuit as a group of resistors alongside of one another. So what I would say is, think about it this way. Imagine there wasn't a battery involved, and we just cut it straight there. We cut the circuit out, cut the circuit with the wire snippers, and then open this up. What would happen is this would look like this. You'd have the 3 ohm resistor, then you'd have the 6 ohm resistor, then you'd be branching off as we're showing up here. Here's the 4 ohm resistor. Up top we'd have a 6 ohm resistor here, a 2 ohm resistor here. They'd branch back together, and you'd have the 1 ohm resistor here. Okay, so again, we're taking this and opening up the flaps in a sense. So this would be the point where we cut it, right? We cut it here and we cut it here, or we simply just cut right there. And what this does is it allows you to see it a little bit easier to simplify. And now what we're going to notice is this. These 2 resistors are in series, so right away we can start by just using our sum law and say that's just a 9 ohm resistor, really. So what we've done already is replaced that first part. Then we'll see that these 2 resistors are also in series, so we're going to replace them with one resistor of 8 ohms. The bottom is still 4 ohms, and then they branch back together, and we have a 1 ohm resistor. Now, we can see that we still do kind of have some things that look like they're in series, but this little mini parallel part in the middle has to be taken into account for. So this parallel portion of the part, we have to use our reciprocal law. And we have to say, well, to simplify this, we can say that 1 over the equivalent resistance equals 1 over 8 plus 1 over 4. Well, 1 over 8 plus 1 over 4 is really 0.375. That equals 1 over Req. So then Req, or the equivalent resistance, is the inverse of 0.375. And that is equal to 2.6 repeating. So the equivalent resistance of these 2, rewritten as 1 resistor, would really be approximately around to 2.7 ohms. So now what we have are really just simply 3 resistors, 9, 2.7, and 1. So if they're all in series now, as we can see, we can just simply add the three together and make the circuit look like the following. One resistor of 12.7 ohms. So let's redraw the circuit that we started with. And we'd have a 9-volt battery, as we had here, with just one resistor of 12.7 ohms. Now, with that said, once we've calculated the equivalent resistance, we can again use Ohm's law. V equals IR. This is the equivalent resistance. This is the total current. This is the total voltage, or the voltage supplied by the power source. So we want the current, so let's solve for I. So V over Req equals I. So the voltage of 9 over the Req value of 12.7 gives us a current of 0.71 amps. So that's the current through the entire circuit.